I'm Erik. I'm instructor for the course Probability and Statistics, which is a very fun course, and it's also a little bit challenging because the goal of the course is to get people from very different backgrounds to sort of more or less get a similar level and understanding of the basic concepts of probability and statistics. So the course starts with another instructor than me, who is going to do probability theory, which is a fairly classical way of teaching with a lot of pen and paper and quite a bit of mathematics. So that's the first half of the course, and that's ended with a partial exam. And then the second half of the course is me and another instructor doing statistics. And our part of the course, the statistics part of the course, is a little bit more or less classical, more maybe more modern, where we don't want to emphasize the mathematics, but we want to emphasize more what's sort of the concepts to understand them at a more intuitive level. And we're going to use the software package R for doing that, to be able to do calculations and to demonstrate what happens. So here we are in lecture number 2. The way the lectures work is that there's this HTML document that I'm showing you now, which has theory, a little bit of theory that we lecture about, and it's interspersed with exercises. So this is an exercise, and in this lecture, we've been talking about estimating, which means that we have data and we try to figure out what a good probability distribution is that could have generated those data. So we're looking for a statistical model of the data. So just to explain some jargon here, we have observations, 20 observations, x1 to x20. Those are observations from, let's say, a call center where they've, on 20 subsequent Mondays, they've counted how many calls came in between 12 in the morning and 3 in the afternoon, something like that. And if you follow the course, then an obvious model for an obvious probability distribution for such data is the so-called Poisson distribution, which has one parameter, a rate, which in this example is set to 2. And now the probability of observing no event at all in this particular time period is the probability that the observation x equals 0. And if it's the Poisson distribution, then that's e to the minus that lambda, so e to the minus 2. And that's the exponential function. And at this time in the first year, you will have learned about exponential functions in the Math for Stats course, but maybe you also know from high school. So let's suppose we don't know that lambda. I mean, it's 2, but we don't know that. We only have the data and we need to estimate it. So we want to try to figure out what is the probability of observing no event at all. And now two obvious estimators of observing no event at all. That's namely looking how many out of those 20 observations is 0. So the proportion of zeros in the 20 observations. That's T1. And the other estimator is more complicated. There we make an estimate of that lambda, and an obvious estimator of that lambda, which will be obvious in the course, is the average of the 20 observations, and we plug that into that little formula. So we take the average of the 20 numbers, and then we do e to the power minus that average. And that's also an estimator of the probability of having no events at all in a particular time period. So two obvious estimators, and they're both plausible. I think the first one, that proportion, is more plausible to you, but then if you've done the course, the other one is also pretty obvious. So that's the first question here. Why are these estimators obvious? And then it's organized in such a way that you're supposed to try your best to answer the questions, but there's also the answers, and you can click on them, and then they will appear. So the course is organized with me lecturing in the morning, or Jelle lecturing in the morning. That's the other instructor. In the afternoon, usually there are assistants that help you with these exercises, but there's also the answers available to you. So why these estimators obvious? Well, I kind of explained that to you. Make histograms of the sampling distribution of the two estimators and align them vertically. So the point here is that there are two obvious estimators. Both are trying to estimate e to the minus 2. That's a number. But which one is better? And the way to figure that out is to try it out. So this little bit of R code allows you to play out this scenario of observing 20 numbers from a Poisson distribution and trying to estimate the probability of 0. So we just tried it out. We use the software R, and by this time in the first year, you will have already several weeks of instruction in this particular software called R. But ultimately, it's reasonably easy to read. So we're going to do this 10,000 times. For 10,000 times, we're going to sample 20 numbers from a Poisson distribution with lambda equals 2. And the first estimator will compute, that's just the average of it's just a proportion of zeros. That's a little bit funny how I write it there. And the second estimator is e to the minus the mean of those 20 numbers. And then I make a histogram of the two. So here you see what happens in 10,000 cases. And you can see that both estimators are about centered at, let's say, 1.4 or 0.14, which is about e to the minus 2. But the second estimator is much more tightly clustered than the first one. The first one is very discrete, very separated out, very spread out. The second estimator is a better estimator because it's much closer to the truth. It has much less variability. And so then in the remaining exercises or the remaining part of the exercise, we'll quantify why that in fact, yes, it's true, the second estimator is better than the first one. So this is just to demonstrate how these problems work. I wanted to show you that there's a little bit of math, a little bit of formulas here. There's a little bit of R code typically, and there's a lot of trying to understand and looking at what happens and trying it out. And you can change the lambda parameter. You can set it to 5 and see if that second estimator is still the better one. And maybe you can try to figure out if there's a third option that you can think of. So that's sort of a mixture of a little bit of math and a little bit of trying out and a little bit of R. And it leaves us with a big question, namely, what is a good estimator? How do you quantify that? How do you compare estimators? And how do you come up with good estimators? Okay, and so that's the lecture that I wanted to show you. So this was just a little introduction. Do you see my other tab now, Gabriele?
Yes, we can see it.
Okay, great. Okay, so this is then 2 lectures later. This is lecture 4, where we're going to discuss a good method of finding estimators. Because, both those estimators in the earlier example were pretty obvious, but one was just a lot better than the other one. So we want, and there is a good method to finding the good estimators in most cases, and that's the method of maximum likelihood. So that's what we're going to explain here. So I recap a little bit. So I say, we saw a couple of estimators, and sometimes an estimator is better than another estimator, and it's really difficult to tell in advance which one is going to be better. So we need a method of finding good estimators. And then here's a little example that I'm going to explain this method of maximum likelihood. So here's a story. You take a peanut, you throw it in the air, and you try to catch it in your mouth. Suppose you do this 20 times, and you record the number of successes. Of course, don't try this at home because you'll maybe choke to death. You don't want that. But there is a proportion of successes. And if you would repeat this very, very often, then that proportion would kind of converge to some proportion that indicates your skill at catching peanuts in your mouth. But we have a limited sample, only 20, and we want to estimate that proportion that you would get if you did this lots and lots of times. Since repeating the whole experiment will typically result in a different number of successes, we should think of X as a random variable. So there's a bit of a philosophical issue. What is randomness? Maybe it only exists at the quantum level. In statistics, randomness, in a sense, refers to things that the fact that we don't have full information. So with catching peanuts, if you know the exact speed with which the peanut goes up, and if you know all the physics, then basically the question whether or not it will land in your mouth is, in a sense, deterministic. But there's small variations, and we can't even measure that if we wanted to. We take a very pragmatic approach by saying that if you repeat an experiment and it's not guaranteed to give the same result, that's what we call random. Okay, anyway, an obvious model for X is the binomial distribution. So something that can be either a fail or a success, and you count up the number of successes, in this case successful catches, a typical model for that is the binomial distribution, which you'll know at this point because you'll have learned about that during the first part of the course about probability theory. So here's a little exercise. Think of some reasons why the binomial distribution might not be appropriate. Because often as statisticians, we have a toolbox, and there's the Poisson distribution in there, and there's the binomial distribution in there, and there's all sorts of standard models. Maybe you've heard about the t-test or ANOVA or the chi-square test, all that stuff. And it's very easy to grab for those tools. But a good statistician or a good data scientist will think about what are the assumptions that underlie these models. Are they realistic? Can you do better? How would you check those assumptions? So this is just a little bit of a question to think about whether or not this binomial distribution, which is the obvious choice, is also a good choice. Anyway, here's the method of maximum likelihood. So suppose you catch the peanut 15 out of 20 tries. An obvious estimate of the probability of success is just the sample proportion, right? So that's the number of successes. 15 divided by the number of tries is 20 is 0.75. So let's see about the method of maximum likelihood. What it does is for every possible choice of the true probability of success, you compute the probability of getting 15 out of 20 successes. So when the true probability of catching a peanut in your mouth, if you're so bad at this that your probability is only 10%, then catching 15 out of 20 is almost impossible. So the probability is pretty much zero. If your skill level, if your probability of catching this peanut is about 60%, then the probability of catching 15 out of 20 maybe is about 0.07% or something like that. Those are different probabilities. If you're super good at it, if your probability is 99%, then catching as few as 15 out of 20 is again very unlikely. So this is called the likelihood function. And if you look closely, you see that the maximum of the likelihood is at 0.75, which is also the obvious value that we found, the proportion. So the method of maximum likelihood says, okay, well, let's check all the possibilities for this for the parameter that we want to know, and the one that maximizes the probability of the data, that's a good choice as an estimator. That's the method of maximum likelihood, and here's a little bit of R code to compute that in a very direct way. We set up a little vector, we compute for lots of different values for that parameter p, compute the likelihood, and then we find the one that's biggest. And you find 0.75. So then there's a little question that, do you think this is a sensible thing to do? Does that make sense to you? Is this intuitive to you? Just think about it. So this is not a question that has a right or wrong answer. It's just a little prompt for you to think about, if this makes sense to you. So the whole text is full of these little prompts, and that's supposed to teach you active reading, because a statistics text or a methods text or mathematics text is not like a book or the newspaper. It's a text that you need to engage with actively. And you need to be constantly, at every sentence, need to ask yourself, does this make sense to me? Can I think of a counterexample? Can I think of another example? How would I do this? To constantly compare what you read to what you know. Is this surprising? Is this what I would have expected? That sort of stuff you need to actively think about a text. And a lot of these little questions are to teach you to do that. Then there's an important point about a terminology. In the probability part of the course, you will have learned that the probability mass function looks like this for the binomial distribution. So there's n the number of tries, x the number of successes, and p the probability of a success. So this expression here says what's the probability that out of n tries, when the probability of success is p, you get little x successes. And it's a complicated formula, it will be explained. The point here is that it's a function of little x. So for every choice of little x, from 0 to n, this expression allows you to compute the probability of exactly x successes, x being 1 up to n. There's another function, which is actually the same function, but viewed differently, viewed as a function of little p, the parameter. And when it's viewed as a function of the parameter, it's called the likelihood function. So that's confusing. It's the same thing, only viewed from opposite ends. One is viewed from the outcome, the little x, and one is viewed from the parameter, little p. It's the same function, but has a different name, and it's used in very, very different ways in statistics. And the method of maximum likelihood is about this likelihood function, and about maximizing the likelihood function as a function of the little parameter. Okay, so then there's some very good advice about computation, because when you have independent observations, then the probabilities of each observation multiply. And you can see this multiplication a little bit in this formula also. So we're multiplying x little p's and n minus x little 1 minus p's, we're multiplying them all together. And if you do this in a computer, and if you have lots of observations, then you're always multiplying numbers that are less than 1, because they're probabilities. And when you multiply lots and lots of numbers that are much less than 1, you'll get very small numbers. And inside a computer, it can only represent small numbers, but there's an end to it. Computers can only represent numbers that are, well, whatever the limit is of your computer, 10 to the minus 23 or whatever. And at some point, it doesn't represent those numbers anymore, or it will start to make mistakes. So the general lesson is that working in computers with very small numbers can get you really big mistakes. And to prevent that, you can work with the logarithm of the likelihood. In the Math for Stats course, they explain all about the logarithm, which is a special function, just like the exponential function. And the logarithm basically turns products into sums. And when you add stuff, even if they're small numbers, then they don't get super, super small. They get bigger and bigger and bigger. So this underflow problem, the problem with calculating with very small numbers, disappears when you work with the logarithm. And maximizing the likelihood is actually the same, when you think about it, as maximizing the logarithm of the likelihood. So here's the likelihood function. It looks a little bit like a skewed bell curve. It's not a bell curve. It's a little bit skewed, as you can see. And here's the logarithm of that same function. It still has a maximum at 0.75. But it looks a little bit, well, like this. And there is a super, super important, the most important theoretical thing in statistics is that logarithms of likelihood functions start to look like parabolas when the sample size increases. So that's called the central limit theorem. You may know about it in the sense that this probability function will converge to a bell curve. Everything ultimately becomes normally distributed, the normal bell curve. And if this becomes a bell curve, then the logarithm of a bell curve is a parabola. And that's a super important theoretical thing that is used a lot to do approximate calculations. So even in this situation where it's not quite a parabola, approximating this with a parabola will already be very important. And one hint of why it's important, you just saw Mark talk about that in the previous lecture, is that Taylor approximations work really, really well with parabolas. Only after 2 steps, you're there already. It's exact. And using a Taylor approximation by something that looks a lot like a parabola will already give you very good Taylor approximations, because it's all pretty close to a parabola. A parabola is a quadratic function, by the way. All right, so there's this thing. You can still maximize it and find 0.75. And then the next section is about computing the Emily. And there's a simple recipe. You write down the log likelihood function of the data, just like I did here, and then you have to find a parameter where that log likelihood is maximal. So that's a way of finding that likelihood function numerically in a very naive and silly way, in a very bad way. So that's what I'm doing here. I simply took values for that little p that go from 0 to 0.01, 0.02, 0.03, lots of different small values. And I compute for all those values, I compute the likelihood function, log likelihood function, and then I find the one that's biggest. So that's a very direct way of thinking about maximizing a function. But it's not a very good way. It's a very slow way, because I spent a lot of time, almost all the time, computing values for that log likelihood that are nowhere near the maximum. So I'm wasting my time. And for this little example, it makes absolutely no difference because it's such a small and easy function. The whole thing is done in less than a millisecond, whatever, and it makes no difference. It's very fast. But when problems become larger, computation in statistics becomes a really, really big issue, and in data science, of course, as well. You're always bumping up against what you can do in your computer, because problems are larger in the sense of larger data sets and in the sense of larger models with more and more parameters. So this little problem has only one free parameter, namely that little p, but larger problems have lots and lots of parameters to be able to model much more complex situations than catching a peanut in your mouth. And also, we often want to simulate data. So like the problem that I started with, we wanted to try out how well our estimator is working. And to do that, I repeated the whole procedure of making data and computing my estimator 10,000 times. And that didn't take any time at all because it was all very fast. But if in there's a computation of a maximum likelihood estimator, and I do it in a very silly way like this, then I can't do that anymore because it would take years and years to go through this whole computation 10,000 times. So there's many reasons why computation is important. First of all, the data sets are bigger. Secondly, the models are bigger with more and more parameters. And thirdly, the fact that we often want to repeat a certain procedure many, many times to get an idea about the performance. So computation is really important. Now, unfortunately, there are two faster ways to compute. The first one is to use the clever algorithms that are in R. So here I'm being very stupid. I'm just for myself doing a grid search, as it's called. I make a grid of little values for p, and computing the log likelihood for all those values. But R has better methods for optimizing. And basically what it will do is compute the log likelihood at some value for p and some values near there, and then get something of an idea of is the function increasing or decreasing there. And when it sees it's going up, it will take some steps in the right direction. So it will take steps in the right direction, sometimes overshooting and tracking back, sometimes undershooting and then taking bigger steps to find that maximum much more fast. So there are very clever algorithms for that. And in fact, optimization is a huge, big deal in mathematics. It's a whole separate field of mathematics to optimize functions fast. And some of those routines are in R, and some, and it's even an active research area. So there's a function in R, and we'll demonstrate that, and we'll show how much faster that is. Because, well, if you do it once, you can't see the difference, but if you do this 10,000 times, you can see a clear difference between doing the silly grid search and using a dedicated optimizer. The third way of optimizing a function, so it's the stupid way and the clever numerical way in R. And the final way is with mathematics, because we know that if you have a nice function, that an optimum of that function, either a maximum or a minimum, occurs where the derivative, the slope of the function, is equal to 0. Right? So if you have a little mountain like this, then the maximum occurs where the slope is 0. So that will be the mathematical way of computing the maximum likelihood estimator in this example, would be to take the log likelihood function, then take the derivative with respect to p. And if you forgot about derivatives, then Mark will be reminding you in the first half of the year. So you take the derivative, you set it equal to 0, and you solve the equation that you get. So that will immediately give you an answer. So it's infinitely fast in a sense because it's immediate, and also you will get a mathematical expression for your maximum likelihood estimator. So you won't just get a number for it, 0.75, but you will get the answer that it's x divided by n, the number of successes divided by the number of tries. And in more complicated situations, you can also hope to get some sort of a formula for that maximum likelihood estimator, and that can be very useful, first of all, for very fast computation, because now you just have to run the formula, and it's very useful for theory, because now you can look at that function and do all sorts of math with it. So there's this hierarchy, and the way also we teach it. The first is this grid search, because it's easiest, it's easy to visualize, and it's easy to understand. I want you to understand what it means to maximize this function. Putting it in an optimizer from R is much faster, but it has the disadvantage that you don't know what you're doing. Or at least you don't have to know what you're doing. It's a black box, you put it in, you get 0.75 out, and you might never even have, you never have to plot this function, you never even have to look at it, you never have to understand it. So that's why we start with explaining this grid search, so that you can see it, you can understand it, you know what you're doing. Then you take the step to optimizing with the routines in R. And finally, in certain situations, you can do the math. But the math has the advantage that you get explicit formulas and that you can compute very fast, but it has the disadvantage that in many situations, you can't do it. The math quickly becomes too hard. And that means that in a course like this, I can only ask you to do the math in very simple situations, and there's like 10 of them, and most of them are in the exercises. So I'll find that very quickly I run of fun examples to ask you at the exam. But if you just have to optimize, then you can do so much more. I can basically get any crazy situation, ask you to write down the likelihood, and if you can compute it in your computer, then you can optimize it. So it hugely expands the range of things that I can ask you and the things that you can do for real. So that's going to be a theme throughout the course, is that we'll do everything with math so much as we can do that without getting too complicated. So in simple situations like this binomial example, we can do the math, we can show you, and it's very useful. But we'll also do these things computationally with R, so that you can actually do something other than very silly, small little problems that are kind of textbook school problems. All right, so that's going to be the course. This is a whole course, actually, for one day, what I just explained to you. And then there'll be a whole bunch of exercises. So these exercises are all little stories. If gene frequencies are in equilibrium, genotypes big A, small a, and small a occur in a population with certain frequencies that depends on one particular parameter. That's called the Hardy-Weinberg equilibrium law. So then suppose there's a population with so many individuals, they've been genotyped, and we've got these numbers. Find the maximum likelihood estimator of that unknown parameter theta. Maximize the likelihood, the log likelihood, and do all that stuff. So that's a typical question with an answer to go with it, all that stuff. So that goes on for a little while. So this is going to be a busy day where you do a lot of exercises, and there will be a very short lecture by me because I basically did the whole lecture already.